Hello and welcome to a playthrough of Stabilizing Transformers for Reinforcement Learning by a team at Google DeepMind, published in 2019. Here we're building on top of a previous paper from the same year by also Google DeepMind and people at Carnegie Mellon on Transformer XL, TRXL. We walked through that in a previous video, and TRXL added two modifications to the vanilla transformer language model that was at the time 7 years ago. These two were segment level recurrence with a stop gradient memory cache and relative positional encoding inside the attention score. It was again demonstrated on language model, and here we're asking whether the same architecture can be trained under reinforcement learning objectives. For language model, the reason they added that segment level recurrence was a cache, was to allow segments, which is a way to fragment the input by specific count of tokens, allow segments to actually share information, because the segmenting didn't necessarily occur at a phrase level or at a semantic meaningful place, and you would perhaps be missing out on context and what attention could pay useful attention to. And then the relative positional encoding was added because once you have this cache from the previous segment, because they were using positional absolute encodings, you would get a clash between the position encodings of the previous segments, which were absolute to its own segment, and the absolute encodings of the current segment that you're trying to add a cache to. So they needed this relative position encoding, which took into account a relative difference between indexes of tokens from both segments. This TRXL is modified for GTrXL with an identity map reordering of the layer normalization and a gating layer that replaces the additive residual. The reordering moves layer normalization to the inputs of each sublayer and inserts rectified linear unit on the sublayer output before the residual addition. So this in its own right gave a huge boost for their DM Lab 30 experiments. So control task with RL. The gating layer then replaces the residual addition with a per position interpolation between the layer's input and the transformer sublayer output. Self-attention had challenged LSTMs in supervised sequence modeling for a while then, but RL memory architectures were still dominated by LSTMs, long short-term memory units. Earlier work had shown that transformers could not solve simple banded tasks or tabular MDPs even, which led the authors to suggest that the architecture was the problem. And the solutions at the time in the supervised literature were long warm-up schedules, specialized initializations, and managed learner rate decay, which were things that did not transfer well to reinforcement learning, which RL is the setting we operate in as an partially observable Markov decision process, where observations are OT rather than full states, and the transformer has to encode the history of observations into a representation that the policy and value heads can effectively consume. At each time step, there are observations, which can be an RGB image on DMLab or a vector for the numpad environment that they created. These observations pass through a small per modality encoder, a ResNet for images, a 2-layer MLP for vectors, and those produce a fixed 256-dimensional embedding that is a common space that both get projected into. And that embedding is what sits at the transformer's input position, and hence the input sequence the transformer sees at time step t are these embedding E1 up to ET, rather than the tokens from a corpus in the case of a language model. And episodes can run for thousands of steps, so the transformer encoder needs effective long-term memory over this. The policy and value heads are updated with value-based MPO, VMPO, which we covered for smaller networks and continuous control in a different video. And it's a non-policy expectation maximization algorithm that works on data from a distributed actor learner. Let's recap the TRXL setup. At every layer, the model concatenates a stop gradient cache M of the previous segment's hidden states to the current segment, and the keys and values are built from these two put together. The queries, however, work from the current segment, so the cache extends what the output can attend to without extending the autoregressive output. So it's internal to the transformer. Position information comes through the relative distance score inside the attention rather than as an additive embedding, absolute embedding on the input, as I mentioned at the start. That gets put in a TRXL block, which has a multi-head attention sublayer followed by a position-wise feed forward with an additive residual and layer norm. The residual gives the network a shortcut through the sublayer, and the layer norm rescales the sum to unit variance. And that is all good for supervised training, but a bit problematic for RL, as we will see. Each block ends in layer norm. So layer norm subtracts the per token mean across the D hidden units, divides by the per token standard deviation, and applies a learned affine, which is non-linear data dependent transform of every token row. The input never reaches the output without being modified. Even with every sublayer set to 0, an L block stack would output L nested layer norms applied to that input rather than the input itself as an identity that can pass through. And hence no choice of parameter makes the deep network start out behaving like a shallow one, which is useful for RL because the gradient signal is very rough at the start, with rewards being noisy and the data distribution shifting as the policy changes because we're exploring different parts of the environment. And hence early updates to layer 1 are often in the wrong direction in RL, and a bad update at layer 1 can enter the next block's layer norm, gets recentered and rescaled together with a new sublayer output, and the resulting corruption just keeps propagating through the network and every block above, and the policy and value has never seen an unaffected and untouched input, while the early layers are still being trained. But it would be useful for them to also learn from that. And that's why they introduced this identity map reordering, which moves the layer normalization to the input of each sublayer rather than the output. Every sublayer now sees a normalized input, but the residual stream is left untouched through the layer. It becomes the original input plus a sum of outputs that have gone through the rectified linear unit across the depth. With the sublayer projection, matrices initialized small. These outputs are near 0, so the deep network behaves just like a shallow one at the initialization, which is what we wanted, and it deepens gradually as each sublayer contribution grows, solving the problem. The ReLU unit on the sublayer output keeps the additive contribution non-negative, which means that the residual stream cannot have unbounded negative drift through the depth of the network. They call this configuration TRXL-I, and this alone allowed them to get a good score on DM Lab 30 with a human normalized score of 5.0, while the TRXL before got a 5 and they got 107, which is already better than the LSTM baseline at the time, 99. And this is before they even added their gating mechanism. So they show that deep memory model that starts as an identity is starting as a Markovian agent. The policy and value heads see the raw observation with no temporal mixing. In RL environments, reactive behavior usually has to be learned before memory-based behavior can be useful. Otherwise stated, an agent has to know how to walk before it can remember where it has walked. And starting near identity supports this order of learning. The depth of the network is something that the optimizer can use as a memory-based behavior to manifest. The gating replaces the additive residual with a parametric gate G, where X is the layer input and it goes into G, and Y as well is the rectified linear unit sublayer output, and they both go into G. Modulated here means that the sublayer contribution at each hidden unit gets multiplied by a sigmoid bounded factor between 0 and 1, and that factor is a function of X and Y at that position. That means that the network can decide unit by unit and token by token whether to open the gate fully, partially, or not at all. The additive residual doesn't have this control. It always adds the full Y, whether or not Y helps that unit, so it gets replaced by this. Initializing the gate to favor X would let the input pass through and recovers the identity path that the reordering enabled us to have. But now the path is content dependent rather than fixed. They do a survey of what types of gating mechanisms they could put in place. So they have about 3 options here. The input gate sigmoid modulates the residual stream and adds the sublayer output unmodified. The output gate does the reverse, passes the residual unchanged and modulates the sublayer output. The highway connection modulates both with a single shared sigmoid and its complement. The sig tan H variant adds a tan H on the sublayer side. The GRU gate adapts the GRU cell with the sublayer output playing the role of the recurrent target. And it is the most expressive of the 5, they argue. And the empirical claim is that their GRU wins on stability, robustness, and overall performance across their ablations. The GRU gate inherits the structure of that GRU cell, untied across depth, which is 2 sigmoidal gates are formed from the layer input X and the sublayer output Y, reset gate R that controls how much of X feeds into the candidate, and an update gate Z that controls the interpolation between X and this candidate. The candidate H is a tan H bounded combination of Y with a reset gated X, and the output when Z is 0 recovers the input, and when Z is 1 recovers the candidate. The bias gets subtracted inside the update gate sigmoid and is what lets the paper start the gate close to the identity at initialization so that the rough information can pass through rather than be corrupted. A positive B shifts that sigmoid argument down, so Z is near 0 before any training data has been seen, and the gate's output collapses to X. The paper sets this B at 2 for GRU variant and at 1 for other variants that they've done the ablation study for gating. The input gate has no B, no bias, and a memory maze ablation, environment ablation toggled the bias on and off and showed that this helped with B equal to the 4-layer GTrXL GRU reached human performance in 2 billion environment steps, while at B0 it didn't train almost at all, even in 4 billion steps. So double the amount of steps and less success. We bring that all together to create our GTrXL block. Each sublayer takes a layer normalized input, produces rectified linear unit output. The residual addition that would have closed the block is now replaced by a gating layer, which interpolates between the sublayer input and the sublayer output. The block has 2 independent gates per layer. One is for the tension and one for the feed forward. Each has its own GRU parameters and identity biased initialization. Combining this across n layers gives the model a controlled depth at every point in training. At initialization, the encoder is close to identity and it deepens as the gates open, as learning happens in exploration. The cache is still concatenated to the current segment with stop gradient, and the recurrence from the TRXL implementation is preserved here. So they take that, and the default architecture over their experiments is a 12-layer transformer with 256-dimensional embeddings, 8 attention heads, each of 64 dimensions, and a 512-step relative position memory cache at every layer. The receptive field at the output of the layer 12 is henceforth 6,144 time steps, which spans most of the 30 episodes, most of the DMLab 30 episodes and environments that they verified against. The training is done as mentioned with VMPO on a non-policy expectation maximization method, and it's done in a distributed actor learner setup. For every architecture in this paper, they sample 6 to 8 VMPO hyperparameter configurations from a fixed distribution, and they report the mean and standard error overruns to complete the 10 billion environment steps for each of the tests. And they show that overall, it does really well. In summary, GTrXL is TRXL with 2 additions. The reordering moves the layer norm to sublayer inputs and adds a ReLU on sublayer outputs, opening an identity path through depth that a post norm block does not have, and that gives us most of the improvement. Then this expensive gating layer replaces the additive residual and the interpolation between the layer's input and layer output is configured through the GRU. Through a positive bias on the update gate, we start near identity. Trained with VMPO on DM Lab 30, the architecture matches external memory baselines that use auxiliary losses and an order of magnitude more environment steps, and exceeded the LSTM on memory heavy environments at the time, and matched it on the reactive ones. And it's overall an answer to the question of if transformers can be used for reinforcement learning and can have working memory in that situation, which I think they've shown effectively. But there's been many updates to these types of architecture since then, but I think this was a good stepping stone to go through.